Hello everyone, I am Dr. Krishna Sarker, Department of Electrical Engineering. Here in this session, I will be going to discuss about transfer function calculation from electrical networks. Linear control systems, this is problem number 1 or example 1. Lecture series on linear control systems, lecture number 13. So our topics, transfer function calculation from electrical networks, and this is problem 1. Transfer function calculation. What is the example or problem? Problem 1. Find the transfer function of the given electrical networks. Find the transfer function of the given electrical networks. This is the resistance R and unit R. Inductance unit, this is L. And this is the source VIT. And this is the connection. V0T, output of the network. And VIT equals to input voltage. V0T equals to output voltage. So this is our example 1. RL network where VIT equals to input voltage, V0T equals to output voltage. Calculate transfer function, that means V0T by VIT, or Laplace transform of V0T divided by Laplace transform of VIT, and all initial conditions zeros. Procedure for finding the transfer function of electrical networks. Solution. Step number 1. The given electrical networks as shown in figure and determine the transfer function. This is the electrical network, given networks, resistance, inductance, and voltage source VIT, and the connection diagram where V0T equals to output voltage. So first, draw the given network in the S domain. In the S domain with each inductance by SL and each capacitance by 1 by SC. So this is our very interesting part. Each inductance by SL and its capacitance by 1 by SC. In this circuit, inductance, so put here S into L. Then next step, use KCL, KVL, mesh analysis, node analysis to write network equations. So in this circuit, this is one loop, this is another loop. So either KCL, apply either KCL, KVL, mesh analysis, node analysis to the right network equation and write the network equation. Next step, solve the simultaneous equation for the transfer function. So at last, solve the simultaneous equation for transfer function. Transfer function means Laplace transform of output divided by Laplace transform of input, and all initial conditions are zeros. So this is the step 1. So step 1, this is the given network, electrical network. Then draw the given network in the S domain. So this is the time domain. So next circuit, draw the time domain to S domain circuit, and where inductance put SL, where capacitance put 1 by SC. Then use KCL, KVL, mesh analysis, node analysis to write the network equation solve the simultaneous equation for the transfer function. Next step, step number 2, apply KVL in mesh 1 of the given network. So what is the mesh 1? This is the given network already discussed. This is the loop current IL, IS, and the mesh 1 equals to, this is the mesh 1. So first write KVL equation, input voltage VIT, input voltage equals to VIT. Next, VIT equals to what? VIT equals to R into IT. This is resistance R and current passing through R, I of T, then R into IT plus for inductance L into DIT dt, rate of change of current, L into di of T dt. This is equation number 1 for mesh 1. Then apply KVL in mesh 2. This is the mesh 2. This is the mesh 2, and mesh 2 output voltage V0T. V0T equals to, this is the V0T. This is the V0T. And this output voltage V0T equals to what? Only capacitor inductance across drop. So this is equivalent to L into DIT dt. L into DIT di of T dt. So this is equation number 1 for this loop. This is equation number 1 for this loop, and this is the equation number 2. This is the loop 2 or mesh 2, and this equation V0T equals to L into di of T dt. Then what is the next step? Then step number 3, taking Laplace transform of the equation 1 and equation 2 with assumption that all the initial conditions are zeros. So what is the equation number 1? This is equation number 1, and this is the equation number 2. So taking Laplace transform of equation 1, taking Laplace transform of equation 1, this is the equation 1, taking Laplace transform for VIT, this is the VIS, this is the VI of S. Then Laplace transform of R into IT, I of T equals to I of S, and Laplace transform of L into di dt equals to S into L into I of S. Why? This is the time domain equation. This is the frequency domain equation, voltage, input voltage, and this resistance constant, and IT, Laplace transform of IT equivalent to I of S, and L constant inductance, and this is the constant inductance, ddt equivalent to S, ddt equivalent to S, and I of T, Laplace transform of I of T equivalent to I of S. So this is the equation number 3. Then taking Laplace transform in equation 2, and we get V0T equals to VIS equals to S into L into IS. So this is the equation number 2, and VIT Laplace transform equals to V0S, L constant, ddt equivalent to ddt equivalent to S, and I of T equivalent to I of S. This is the equation number 4. This is equation number 4. Then step number 4, definition of the transfer function. What is the definition? Transfer function equals to Laplace transform of output divided by Laplace transform of input, and all initial conditions are zeros. So what is the transfer function definition? Transfer function definition, Laplace transform of output divided by Laplace transform of input, all initial conditions are zeros. This is the definition. And another form, Laplace transform of output response or effects divided by Laplace transform of input variable or excitation. This is also called the cause, and all initial conditions to be zero. And this is called transfer function. So calculate the transfer function from equation 3 and equation 4. So this is the step number 5. What is the step number 5? Calculate the transfer function of equation 3 and equation 4. And we get VIS equals to RIS plus S into L into IS, and V0S equals to S into L into IS equal. This is equation number 4. So output by input. What is the output by input? V0S by VIS. V0S equals to output voltage and VIS equals to input voltage. So this is equivalent to S into L into IS divided by R into S plus S into L into IS, I of S. So this is the output voltage. And this part input voltage. So ratio output divided by input, and obviously all the initial conditions are zeros. This is the output part, and this section input part is a denominator part actually. So this is the denominator part. Then this is equivalent to common I of S, then cancel I of S, then ultimate V0S by VIS equals to SL by V0S by VIS equals to SL by R plus L S into L. R plus S into L. This is the ratio between output voltage divided by input voltage, where all initial conditions are zeros. So proper transfer function. From the transfer function, if R equals to 1 ohm and L equals to 1 Henry, from the transfer function, R equals to 1 ohm and L equals to 1 Henry, then we can write V0S by VIS equals to SL by R plus S into L. I put here L equals to 1 and R equals to 1. We get S by S plus 1. This is the transfer function. And from this transfer function, numerator terms, this is the numerator value and this is the denominator value. And numerator gives zeros of the system, ZDROS, and denominator gives poles of the systems. Poles of the systems for this particular transfer function, where S equals to 0, numerator part, that means at origin 1 0 and S is equal to minus 1 1 poles. S is equal to minus 1 1 poles. So next, this is the form of M equals to N, and case number 3, M equals to N means number of, if the order of the numerator polynomial is equals to the denominator polynomial, the transfer function is called proper transfer function. This type of transfer function is called the proper transfer function. In this case, numerator polynomial power 1 and denominator polynomial power also 1. So M equivalent to equals to N. If numerator polynomial equals to M equals to 1 and denominator polynomial N equals to 1, then M equals to N is called the proper transfer function. This is case number 3. So V0S by VIS equivalent to S by S plus 1, already discussed here. Number of zeros equals to the number of poles. Number of zeros equals to number of poles. The above transfer function having the simple poles are at S is equal to 1. S is equal to 1, that means S plus 1 equals to 0. S plus 1 equals to 0. So S is equal to minus 1 poles, and the zeros are at S is equal to 0. That means at origin. Then what is the pole 0 position or configuration? This is the real axis. This is the real axis, and this is the imaginary axis. This is the imaginary axis. Then at origin, that means S is equal to 0, 1, 0, and S is equal to minus 1. This is the minus 1 position, 1 poles, and all the poles and zeros left hand side of the S plane. So system will be stable. all the poles and zeros left hand side of the S plane. That's why system will be stable. Then pole zeros of a transfer function. What is the concept? Pole zero concept. What is the pole zero concept of the transfer function? The transfer function of a control system is defined as the ratio of the Laplace transform of the output variable, response or effect, to the Laplace transform of the input variable, that is excitation or cause, assuming or provided that all the initial conditions to be zero. This is the definition of the transfer function. A zero is indicated by a small circle, zero, already discussed. The points at which the denominator polynomial P of S equals to zero are called the poles of the systems G of S. In this particular problem, at S is equal to -1, one poles only. A poles are indicated by the small cross. This is the cross for poles, and this is the zeros for small circle. This is the small circle for zeros. A zero, the transfer function G of S becomes 0, and at poles it becomes infinity. The denominator polynomial of the transfer function is called the characteristics polynomial. It's called the characteristics polynomial. So thank you.